for the first part of computer vision. Or if you have any questions.
Thank you very much for this interesting lecture. So far, there is only one question, how and whether they can get the presentations from the slides from the presentation, our participants. Can we share?
So I believe that first of all, before we share it, this entire stream will be uploaded in YouTube, right? So
Yes.
that is one source of where they can get this information from. And the slides, I think we can also provide, but we'll have to arrange how to do that exactly. And maybe somewhere on the website we can include the slides. I'm perfectly fine with sharing the slides.
Okay, so let's say that we will share the slides and we'll let you know, guys, how we will do that when the jury decides. Okay, thank you very much.
Yes, please. Let's continue.
So continuing on, let me share my screen. Can you hear and see? Okay. Okay, very good. So I will continue the next part of computer vision, which is part 2. And in this block of the presentation, we will look at additional methods, particularly those which are very modern and more or less ubiquitous nowadays in traditional and deep learning based vision. So in particular, we'll look at the vision transformer, which has become kind of the default backbone for many, many models. Additionally, we'll look at diffusion, the diffusion paradigm for generative modeling and for image generation. This is pretty much what you see in all kinds of text-to-image models nowadays. And lastly, we'll discuss briefly about multimodal architectures. So these are architectures which work with different modalities of data, for example, text, image, and so on. So let's start with the VIT. So we saw in the NLP lecture that attention is a very useful thing to have in your model because it offers an inductive bias. This inductive bias represents the idea that we should interpret tokens based on the semantic context with respect to other tokens in their neighborhood. And this turns out to be very useful. So the question comes, is it possible to apply this inductive bias of attention also to vision? And in principle, to follow the same exact process that we followed in NLP, we need to solve 2 tasks. We need to define what is a token, what will serve as a token, and we need to define how we will extract tokens from an image. This is basically the tokenization process. Now, the computer vision community has converged on how to do this, and the blueprint for how to do this is given by the VIT architecture. VIT stands for Vision Transformer. And according to the VIT architecture, a token is defined simply as a patch of pixels. For example, a patch of 14 by 14 pixels, along with their values and channels and so on. So this is a token in the context of vision. And for the second task of tokenization, our process will be to simply cut the image into many non-overlapping patches. So let's see the vision architecture. As we can see here, we have an input image, which gets cut into multiple square patches of pixels. So this is one patch, this is the second one, third one, fourth one, and so on. They are non-overlapping. Then they get flattened, like we see here. Flattening here means that we lose any two-dimensional structure to them, and we just treat them as a sequence of visual patches, like this. So the intensity, the pixel intensity values from each one of these patches gets projected using a linear layer to obtain an initial latent vector, which represents this patch. And this happens in parallel with all the patches. Subsequently, we apply what's called positional encodings or positional embeddings. These are additional features which come from the position of each patch. And it's all very similar to transformers in NLP. So all of these embeddings, they get fed into a transformer encoder, which has self-attention and cross-attention, and in principle has the same structure as in NLP. And finally, we have a task-specific MLP head, which may be for segmentation, for prediction, for classification, all kinds of tasks are possible. So in code, the architecture is very straightforward. The image comes in. This is the image. We extract patches, also known as visual tokens. To each patch, we add the positional embeddings, which contain positional features. So where this particular patch is compared to the whole image. All these tokens, which have been augmented with positions, are fed to the transformer. And at the end, we have a bunch of layers which predict whatever is of interest, for example, classes. How does the tokenization work? It's very simple. It's literally, as I said, just cutting up the image into patches. So what happens is that you receive a stack of images. So B is the batch size, C is the number of channels, RGB. This is the total height of each image and the total width. And the total height gets cut into the patch height, usually 14 by 14, 16. So this is the patch height, and this is how many patches fit into the total height of the image. So same here, you cut it this way. The total number of patches gets flattened after this rearrangement. So that's why you see here H and W, and all the pixel values within the patch, they form the dimension of the token. So as I said, the problem is that just a single patch here, the model does not really know that this patch is in the top left of the image. So that's why we need to augment this patch with positional information. And we follow the same logic as in NLP. So we have positional encodings, which are sines and cosines of the index of the patch. And these features can be pre-computed. They can be stored beforehand. So it's they're very efficient to calculate, and we just add them in an additive way to the actual patch tokens. So And pretty much this is all that is important to say about the VIT. So I'd like to stress that VITs work by mixing information from one patch token to the other patch tokens. And typically, the gain in performance comes from precisely this, establishing correlations between different visual tokens from one end of the image to the other one. And this is very important when it comes to image generation, because if you want to generate an image of a person, of the face of a person, obviously you want to have the eyes of the person be of consistent color. They want to be of the same color. So in this case, you want the visual features for one of the eyes to attend and to sufficiently mix with the visual features of the other eye. And there are all kinds of symmetries. For example, faces are symmetric. So in that sense, you need your visual tokens from the left part of the image to attend to those corresponding tokens on the right side of the image. In general, smaller patches lead to more tokens being processed, which increases computation time and inference. More transformer layers, as in NLP, typically improves performance, but also increases the inference time. And lastly, if we increase the latent dimension of each patch, so this would be basically the hidden dimension here in the transformer. This is like providing more power to the transformer, so the representational capacity of the model increases at the cost of being slower to infer. So VITs, as I said, they've become more or less ubiquitous in computer vision. They have found applications in all kinds of tasks. So here I would like to highlight, for example, object detection. So object detection is the task of locating and identifying any objects of interest in the image. So we can imagine an architecture in which we apply a convolutional neural network first to the image. We extract some convolutional features, which are, again, two-dimensional feature maps. So they can be, in principle, cut into these visual patches, and they can be fed into the transformer encoder. So in that case, each of these patches will attend to all the others. And throughout the layers, information will get sufficiently mixed together, and this will produce patches which are more meaningful, more semantically meaningful. Typically for the decoder, we can have a similar kind of scheme where we start with some queries, and each query attends over these augmented processed patches from the encoder. So this is a very typical kind of design pattern for these kinds of models. And at the output, we have, again, a task-specific head, which predicts the bounding boxes and the classes of the objects. Okay, so VITs are very useful, and they have also found applications in image generation, specifically in diffusion models. So let's now discuss the second subtopic of this block, which is diffusion. So I would like to highlight that diffusion and, in general, image generation is intrinsically tied to denoising. So you can imagine that I give you here a noisy image, and your goal is to denoise it. So the thing is that if you select one of these green pixels, you don't really know what the actual pixel value should be. So, of course, you can make a very intelligent guess based on the surroundings, based on prior knowledge from a data set and so on, but you don't really know what the value should be. So you can see that even this kind of denoising can be thought of as generation, although very constrained. And you can see that if the noise of the image kind of overwhelms any actual signal, so if we have so much noise that this fish becomes invisible to us, then coming up with a clear image is much more like the generation that we are used to. So this is much more kind of like generating an object out of nothing. And precisely this is the strategy that diffusion models follow. So in diffusion models, we will train a network to denoise from noisy images to less noisy images, and preferably to entirely clean images. And the thing is that if we start from a noisy image like this, where you can still see the outlines of an object, like in this case, a person, then it's still generating a clean image. That's what we expect from the model. And if we start from something where the noise completely overwhelms the image, then it should be able to generate images which are entirely consistent and more diverse with this initial noisy image. Yeah, so diffusion in general, this kind of strategy requires three things. It requires a proper dataset and a model. It requires a forward process, which typically adds noise to the image for the purpose of training. And it requires a reverse diffusion process, which is what we use to generate an image by denoising an initial noisy version of it. So the forward process, we can see it here. We can start with a clean image, for example, x0, and we can, in many steps, iteratively add noise to it, such that it becomes more and more noisy. So we'll do this in a very controlled and parameterized way. So we'll set this process to run up to t steps. Typically, this is 1000 in practice. And this kind of process forms a stochastic process because it's an ordered sequence of random variables, where the next one depends on the previous one, which depends on the previous one, and so on. So the forward process is parameterized from 0 to t, from time 0 to time t. And depending on various mathematical conditions, we can get some very useful things and properties out of this process. So in particular, if we want to sample this noisy image at time t equals 3, we don't really have to run the process for 3 steps. We can calculate it directly. This comes from the mathematics of the process. We don't have time to go into the details here, but you have to take my word for it, and believe me that it's possible to skip these steps and sample directly from each point. Similarly, another useful thing is that at the end, again, depending on the mathematics, at the end, it's guaranteed that this noisy image will be sampled from a standard Gaussian distribution with mean 0 and standard deviation 1. So this is the forward process. Now, the backward process is, again, slightly more convoluted in terms of mathematics, but it's still fairly straightforward. What we want to have is we want to have something like this. We start with a completely noisy image sampled from a normal distribution with mean 0 and standard deviation 1. So this is the noisy image at the last time step, t, and we want to periodically refine it up to time step t0, where we will eventually get a clean image, as seen here. So how do we do that? The thing is that, again, coming from the mathematical parts of it, the denoised image given the next time noisy image, next step noisy image, is not Gaussian. So this distribution is very, very complicated to model. However, if we condition on the clean image, it becomes a Gaussian. And this is the strategy that we will use for diffusion models. Essentially, in time step t, we have this image, xt, and the question becomes, how can we get an estimate of x0 so that once we have the estimate, we can sample from xt minus 1. And typically, the model that we will learn will be predicting the noise, which, when added to x0, will give us xt. So this is what the model predicts. The model predicts the noise such that when added to x0, we get xt. And obviously, if we can predict accurately this noise, we can just subtract it from xt and get x0. So this is the strategy that we use. The model will be essentially indirectly predicting x0. And once we have this, we just sample from this distribution, which is Gaussian. And we repeat this process for many steps. So just to show you that it's not very difficult, let's say, we can discuss the training and the sampling of the diffusion model. So at training time, we sample initial clean image from the dataset. This is x0. Now we choose diffusion time step. For example, x2. So the time will be time step 2. And this controls how much noise is added. Then we compute the noisy version of the image from the clean version. So x0 is the clean one. This calculation here gives us the noisy version. Once we have the noisy version, we give it to the model. This is the model. It's a function. And the model gives us an estimate of the noise. And this estimate gets supervised by the actual noise that we have added. So this is the loss. It's pretty straightforward. Now for the sampling, again, we start from complete randomness from a normal distribution. And for t steps from capital T to 1, we call the model, which gives us an estimate of the noise. This calculation gives us an estimate of x0. And finally, this calculation gives us a sample from the denoised distribution. And that's how, starting from this, we periodically resample and resample and resample until very gradually we can obtain images. Okay, so as you can see, this is how diffusion sampling works in practice, starting from random noise and refining this noise. We can see how the outline of an object starts to appear, and typically this outline gets further and further denoised, further reshaped and refined until we actually see something very meaningful, like an object. We can also see here with faces. So if we start with this noise sampled from the last time step, obviously we can get very different samples from it. Oh, very, very different. So if we start from something which is, again, noisy, but less noisy, so from time step 750, you can already see that there are patterns in the samples. So in this case, glasses, people wearing glasses. If we start with this noise, again, noisy, however, less noise overall, you can see that the variations in the samples are quite small. And furthermore, if we start conditioning more and more on the face of this person, we get less and less variance in the outputs. So this is all consistent with what we saw back here in this slide, that we are ultimately denoising, and the more we are denoising, the more we are generating from the sample of possible images. So in practice, diffusion models tend to be quite large. Remember that we have to predict noise, and this noise has the same shape as the image. So it's typically of the same shape as the image, which forces us to use a UNet architecture or some kind of autoencoder, but a UNet is very, very standard. It's also a slow process at test time. So we can use various tricks like doing diffusion in the latent space or adopting a more sophisticated schedule, which can in principle skip some of these steps. However, this is more of a kind of research question, how to do it in a way that's efficient. And we can also condition our generation based on text. So as we saw this diagram already. This is stable diffusion. We have the features from the image coming in here. We have the noise amount. So this would be the diffusion time step T, which has been sampled here, T. And we have text information. So text would be the prompt that you're giving to the model. And this text is ultimately combined in the cross attention of the models. There is really no other way to combine this text with the vision apart from simply sufficiently mixing the features of both. And yeah, different models obviously do the details in a different way. But this is quite standard to have the text embeddings enter in the form of keys and values in the cross attention. Okay, so let's briefly talk about multimodality. So multimodal methods refers to methods which can accept data of different modalities. For example, both an image and some text. And typically the output is also text or image. So these are very useful, obviously, because we can combine modalities and we can extract and reason about things across different modalities. So compared to unimodal architectures, multimodal methods have 3 additional questions that need to be answered. First is how to extract features from each modality. How to extract features. Second is how to fuse them. Fuse them means sufficiently mix them together such that the attentions can attend between them, for example. Third question is when to fuse them. So I won't be discussing this, but there are different options. We can fuse them earlier in the architecture, we can fuse them later. And typically all these things have different trade-offs in terms of capacity of the model and inference time. So in terms of how to extract different features from different modalities, the most straightforward answer I can give you is that each modality requires its own specific encoder. because different modalities can be quite different. Digital images, as we saw, they're very high dimensional. They have data points which are regularly spaced along a 2D grid. Text, as we saw, is discrete in nature. Typically, we have a discrete alphabet of symbols which can generate a discrete number of sequences. So text can be, for example, very sensitive to the presence of some tokens or not. Networks, they have completely different geometric properties. For example, it's all about what is connected to what in them. So all of these things have to be encoded in a way that respects their constraints, so to speak. So how to extract features from different modalities? The question, the answer is that we do it using specific encoders for each modality. So how do we fuse then? How do we fuse from different modalities? I'm going to show you a few methods. Some of them are basic, some of them are advanced. So Clip, for example, is a very early method. It's shallow in the sense that the features which we extract from the text and the image are not really fused. They are not mixed together, but we just make sure that the feature corresponding to an image is similar as judged by, for example, some kind of distance, like the cosine distance, similar to the feature from its corresponding text description. So what we want to have are features which, when compared, they give a high score, high similarity score. But when we compare the feature of this image with this test, with a different text description, these features should be fairly different. So this is intuitive, lightweight, and shallow, as I said. Stable diffusion fuses information in a slightly more clever way. So the text description comes in from here. It's provided by the user. It gets encoded into a text encoder, which gives us some form of latent vector. And this latent vector enters at many places. Enters into the cross tension, like we saw back a few slides ago. So this is a way to, again, to sufficiently mix the text features with those of the visual features. And ultimately the loss which trains these models. The loss is the kind of the thing that makes the model learn which features to attend over and which to abstract away. And finally, there are some methods which fuse information from different modalities in a very sophisticated manner. So let's say, so you can, in principle, train a transformer which takes the visual tokens from an image encoder and modifies them into the text tokens of a LLM. So this is entirely possible. It's not easy, and I just want to show you that it's possible. But this is kind of what happens. So you have image features coming in from here. You have some initial visual queries, which, along with the text queries and text tokens, they get processed to obtain new visual queries, which have the same format, the same shape as the queries which are accepted by an LLM. And typically, this kind of adapter architecture is what modifies the tokens from one modality to the tokens of another one. Okay, I would like to maybe finish here and